Okay, we'll be having a presentation from Hubert Wagner. Hubert Wagner is a assistant professor of data science in the Department of Mathematics at UF. His area of expertise is in topological data analysis, and his work on topological methods for analyzing artificial neural networks has been supported by Google under the Research Scholar Program. So.
Yeah, no, good. Okay. So let me show you one interesting scenario. This is my best version of a self-driving car. So could we? Okay, so let's say this is a self-driving car. It's controlled by this black box here. So I think about this as some kind of artificial neural network, some kind of vision model, connected to this camera. And, ideally whenever such a car sees a stop sign, it would be reasonable to assume it would actually stop. So we can agree on this, but there are quite practical scenarios in which doing something as simple as placing a post-it note on the stop sign would cause the self-driving car to, for example, speed up or whatever else. Some malicious third party decided to, the car to do in the situation. Of course, it doesn't have to be literally a post-it note. It could be anything, added in the real world to whatever this vision model is supposed to perceive. I guess, any even more scary situation is that I point a laser pointer, maybe just a point or more elaborate pattern, and then I can control such a car like this. So this is obviously a scary situation, and the talk will be about trying to look into those this black box and trying to detect if such a model may have been tampered with, allowing this kind of situation. So this is a scenario we looked at in this paper, topological detection of Trojan neural networks. So this was work with Songzu Zheng, Chao Chen, and a couple of other authors. Since I think it was mentioned I'm at the math department, I want to regain some credibility regarding the practicality of whatever I'm talking about. So we published this at NeurIPS some years ago. So most of what I'm talking about will be based on this. So it is a couple of years old. Some of the things are new. But I think this is a really interesting and kind of scary scenario. And the methods we use here are kind of unorthodox. So most of you, I'm presuming most of you never saw the methods I will be describing, and definitely, definitely not in such a context. So the plan, I would like to talk a little bit more what's exactly the setup for this type of attack, which is called the Trojan attack on artificial neural networks. I want to briefly mention some neuroscientific principles, very basic, that kind of guided us in trying to analyze this model. And then I will sketch a setup for a detector, which will be based on not on like usual methods based on things like linear algebra, graph theory, other basic things, but our detector will be based on topological properties of something derived from the network. So for many of you, this could be the main novelty, and this part will be really the focus of the talk, and then I will mention the results, to what extent this thing should be good. Okay, so the setup is that someone is able to poison the training data, which is kind of a strong assumption. Um, I remember last time I talked about this to students. Some students were like, but how would anyone be able to do this? Like if you work for Tesla, like this is your dream job, and why would you, try to do something malicious? I think it's becoming more and more reasonable to assume that someone would want to do something like this. So the idea is that, to the training data, so let's say those are images, a trigger pattern is added, and additionally, the attacker has a capability of also altering the label. So maybe we'll put up this image, and the correct label will be, to speed up as opposed to stop. And in the setup, if this is done properly, then there is no change in the performance of the model on the clean, on the unaltered input. So if so the network may well, as usual, in typical situations, and then someone, points a laser pointer or whatever, and the behavior changes. So it's very difficult to detect. On the other hand, if the attacker wants to, they can exploit this attack whenever they want upon deployment of the model. So, for example, when literally the self-driving car is driving. So it is an important problem in security of AI, let's say, to be able to detect, prevent such attacks. And our goal is exactly to detect. So given a neural network, we want to detect if it had been attacked in this way. We are assuming that we have access to some of the training data. We don't know which of the examples are clean or poisoned, but we have, we're essentially, we want to verify if taking the network and the training data, we want to verify if a given model may have been tampered with. And we do this in a limited data setting, in the sense that we're not assuming we can show large amounts of data to the network. We'll just show it a very limited amount of data. If you have unlimited data and unlimited time to do this, there are very inefficient but effective methods of doing this. You're in this kind of more practical scenario when you want to do this very quickly. Another goal, which is kind of not really in this paper, but I think it's really interesting, is we may want to kind of heal the network. Maybe we may want to efficiently reverse this process. So those would be our two goals. And when we started thinking about this, we actually started from some basic, essentially neuroscientific principles, going all the way to the experiments of Pavlov, which go back all the way to the late 19th century. So I don't know, like how many of you are familiar with this experiment? So it's a well known, but maybe not universally known. So the setup was, so Pavlov was in particular studying dogs, and one thing he noticed is that when those dogs are served food, they salivate, to prepare these, for digesting it. And his idea was to ring a bell, whenever food was served to those dogs. And after doing this repeatedly, he noticed that now in the absence of food, whenever he would ring this bell, dogs would still salivate. So, the observation is that providing those two stimuli concurrently at the same time made some structural change in the brain. And in a sense, you can maybe slowly start to see that this is to some extent similar to our setup. In a more modern language, I mean, you can also appreciate that this is very similar to this paradigm of Hebbian learning, which goes way back to Heb, 50 years later, which is, essentially one of the underpinnings of modern machine learning, let's say. And it's often abbreviated, kind of simplifying the situations that neurons that fire together are wired together, so that if there is a simultaneous activation of neurons, they will, a connection is more likely to be formed, which is kind of another take on what Pavlov really noticed in this particular situation. So, with those kind of basic things at the back of our mind, we started to think about this Trojan training, this Trojan attack, in which, the special trigger pattern is introduced along with those fake labels. We think about this as this kind of situation. And so what we would like to see in the network is some structural changes, in particular from the perspective of co-firing of neurons. So we're assuming that in a Trojan network, the structure of co-firing of neurons will be different, just like in the case of the dogs. There was this co-firing happening when the bell was rung. It's not exactly clear, what. So one thing I should say when I say structural, obviously the architecture of a network will not change. In the simplest case, maybe in the really simplest case, maybe we just consider a simple model like an NLP, and then obviously this attack is not changing the architecture of the network. In practice, we did this with models based on CNNs. So obviously, part of the network is fixed. But what we believe would change would be some co-firing patterns of neurons, or the context of CNNs. Also, we were expecting to see significant changes in the feature maps that we look at. But this whole setup is pretty much agnostic to the actual neural architecture that we use. So the idea is that we will take the network and we will show it a limited number of images, and we'll record the activations of neurons. This is all we're allowed to do. And again, the idea is that the structure of activations will be significantly different for Trojan networks. So in pictures, we focus on, this is a single neuron of the network. We show it all the images in a sequence going, index from 0 to n-1. So we have n of those images, and we think about the activation strengths of those neurons kind of as a histogram, which we additionally normalize in some way. So now we can think that each neuron becomes a point in n-dimensional space, and specifically, I want to think about each neuron as a probability vector, or a discrete probability distribution, if you prefer. But I really want to think about this process done for all neurons. I really want to think about it as a set of points. I would really want to think about this geometrically, except I'm kind of restricted to this probability simplex just because all coordinates are supposed to sum up to 1 and they're non-negative. So I'm really restricted to this lower dimension subspaces. Oh, by the way, whenever there are questions you should ask, so I actually never gave this talk to wide audiences, in particular audiences without some knowledge of topology. So in a moment we'll start talking about that. So if something is unclear, you should probably ask. And I mean, so the idea, which is kind of wishful thinking. So again, we think about each network as a set of points. And if we think about this geometrically, then our assumption is that there should be a visible, very visible geometric topological structure. So there should be differences in the geometric topology and structure of the Trojan networks and the clean networks. So, whatever this means, I will clarify what exactly we mean here in a moment. But if you think about this, it is kind of wishful thinking because it seems like, we want to compare those two sets of points, but then, each point corresponds to a neuron, and the neuron will play a completely different role in different networks. Even, like outside of this Trojan scenario, I mean, if you train literally the same network on the same data, because of, random initialization, you will, in a sense, you will get completely different networks in the sense that you cannot say, oh, this neuron does, exactly the same thing in all those networks. So, so it's not obvious how to really compare this geometric view of those networks. In particular, doing something silly like, just comparing kind of neuron by neuron or, point by point really makes no sense. We would really be comparing, apples to oranges here. So, in our wishful thinking, we're assuming that we would have a method that, first of all, is invariant under permutations of points. So it doesn't care how we permute the points. So we shouldn't assume any kind of bijection between the points or any kind of matching. It should be kind of robust because it's not like, those neurons will behave exactly the same, even if we could find some kind of correspondence between them. And geometrically, we should also abstract away from boring things like, rotations, translations of this geometric object. This is not crucial, but in general, it's something we want from those methods. Maybe in this case, it's not so crucial. Maybe those two are more important. And
I have a small question for Ross, right? So you said they're invariant on the locations and translations. So does that mean like a network and like a set of points that represent a network, if rotated by some amount, will be the same as like the original set of points?
Yeah, so we want to, so it will be more clear in a moment. We will devise some kind of fingerprint for each network, and we say that we want to abstract away from those different things. Yeah, that's a good question. And I mean, so like I said, in a sense, like let's say 10 years ago, this would be kind of a wishful thinking, but this is actually a perfect problem for methods that, we have been developing within the field of topological data analysis. So a while back, this was a completely niche field, and no one outside the field knew about this. It has been getting slightly more popular in the last years. Anyone heard about this before? Yeah, so it's a lot of progress compared to what the situation maybe 10 years back. So I would like to briefly walk you through some basics of topological data analysis, which turns some of the methods turn out to be really perfectly suited to this type of problems. And I like that, I like talking about this because, in a sense, I had been working for a long time on methods suitable for analyzing high-dimensional data. Well, both high-dimensional and low-dimensional, and there have been really nice applications in this low-dimensional regime. but for a long time it was not clear if working with high-dimensional data would be practical. So this was, to me, this was kind of a breakthrough, which showed that you can, there are practical scenarios in which those methods can be applied. And the crucial step was that, telling something topological about the data itself is high-dimensional data itself may not be so interpretable or so useful, but when this data comes from a network, then you're saying interesting things about the network as users. Okay, so what is it about? If you see this, what do you see actually? Yeah, so I agree. If I do this, yeah. So I mean, it doesn't really matter. If you kind of sample this slightly differently, we can agree that nothing really changed. Maybe I move it. I mean, obviously it's still on our keyboard. How about this one? Is it the same? Or it's smaller, yeah. So this is a crucial observation. Our method should not be invariant under scaling, because in our case, scaling maybe the subset of our data would correspond to, for example, decreased activation. So this is not something we want to abstract away from. And there is a very nice method coming from mathematics, specifically algebraic topology, which can characterize essentially shape of data. So if we have this teapot, and I kind of remove the one part to make it easier to kind of to talk about, then if you think about this, it's one basic thing you can tell about it is that it's all in one part. It has this handle you can grab, and if you pour water inside, it will not. So in a sense, it is watertight. It contains this void inside, which allows you to store water. And this is exactly what in topology, what something called homology groups capture. So given an object in Rn, what's often referred to as H0, so the zeroth homology group, simply tells you what are the different parts of your object. So this is supernatural. What this H1 will identify panels or handles like this one, or in other words, more abstractly, it detects those type of loops, which kind of encircle all in your object. And in this case, this H2 will tell you if there is a void, how many voids, and and where they are in your object. So in this case, there will be a void inside. So this is this is something from which normally would be thought as pure mathematics, but it's becoming, those kind of things are becoming useful. The problem here is that here I just showed you the sample, and here we have a kind of continuous object, which is not something you would normally have in the context of data analysis. So how can we kind of bridge the two things? So in this example, we have a much smaller set of points. Let's say they live in Rn in general, but obviously here they're in R2, and I will often call such a thing a point cloud. Point cloud is just a set of points, usually finite. So again, we have seen that we can kind of squint and see some kind of structure like with the teapot. Here is a boring example, but this act of squinting, we can kind of simulate by replacing this, by replacing our points with balls of a certain radius. And here, when you do this, instead of thinking about the points, we can think about the shape of the union of those balls. So I take the union of all those balls. The colors got really weird because my tablet is black and white, and I didn't see that I was changing the color, but you can see well. On the other hand, we're talking about topology in the context of neural networks. So maybe it's not as jarring as I would think. So now we replace, our original point cloud with this representation, and here we can apply this idea of homology. We can talk about those topological features. So here, it's one part, and we have this call here, which is surrounded by this one-dimensional cycle, which is always the green, kind of striking feature here. And I mean, if you're a mathematician, you should also, really appreciate that we went from something which is finite to something which is unaccountably infinite, because now we just have a subset of Rn. So I mean, this is great. And especially for computations, right? Like if you have something which is unaccountably infinite, it must be great for computations, right? Yes. Perfect. And now, so the idea is that, it would be a problem. We couldn't even store this thing really and, manipulate it. But there is a very nice construction coming from algebraic topology, which is called the NeurIPS. And it's very simple. Whenever you, two of those balls have a non-empty intersection, you just put a segment. You could think about it as drawing an edge between the centers of those balls. So whenever we have an intersection, we do this. And what I'm saying is that now I essentially have this graph. And what I'm saying is that it captures the shape of this union of balls. So if I now think about, in particular, how many components there are here and how many one-dimensional cycles, so essentially poles, there are, then I'm saying that this and this graph have the same topology. Uh-huh.
I don't know because why the so happens that become recommended. They remove some figures, all have different figures, and one of the others is happening.
Uh-huh. So we have this triangle here because because this guy intersects with this one with this one, so they all pairwise intersect. So we put an edge whenever they pairwise intersect. So this is what we get. Uh-huh.
Oh, yeah. So you said the topology is the same.
Uh-huh.
Like, what's up there? Where the spine?
Uh-huh. So the pole is, surrounded by this cycle, and here there is a pole surrounded by those edges. So we kind of, have a simpler version of this.
Is there a second bone behind it?
Yeah, so someone does pay attention. So there is another pole here. So if we just do this, if we just think about this nerve as a graph, this is not true. But the trick is that whenever we have a situation like this, which you noticed, we kind of fill in this triangle. And then it's no longer a graph, but this is something called a simplicial complex. So it's like a graph, but then we also have triangles, tetrahedra, and so on. So now this will be our representation of the data in the form of the simplicial complex. And now we can agree that, now there is no hole here because we kind of filled it up with this triangle. So now really the two coincide. Okay. But to do this, we would have to kind of fix the radius, which is how would we choose it? And the idea is that we don't choose it. We just go through all possible radii, going from 0 to all the way to infinity. Which seems like a horrible idea that again it would be uncomputational. But it turns out that only finitely many radii will matter. So this it is definitely computational. We everything I'm talking about we did implement and compute for this paper. And then what we want to do is we want to track the birth and death of those topological features of those balls. So at certain radii, they will appear for the first time. This is the first time where we get this one-dimensional cycle here. And then at some later time, at some larger radius, this hole gets filled up when those balls are slightly larger. And then with this idea, we can track all of those features, and we encode them as this object, which is called a persistence diagram. So each point here, the coordinates of each point correspond to the radius of birth and the radius of death of a single topological feature. So essentially a single hole. And we will think about this as the geometric topological descriptor of our data. You could also think about this as some kind of fingerprint, geometric topological fingerprint of the data. You could even think about this as some kind of hash, that will capture the crucial properties of our data, or in this case, a network. And it turns out that those persistence diagrams have all the properties that we want. They are invariant under, rotation of those points, also translations, and also under the impermutations of the points. Additionally, they are stable, which I will explain in a moment. And perhaps surprisingly, you can form a metric on them. So there's going to be a distance between pairs of those guys, which will form a metric. So as for stability, it's the technical statement is technical, but the idea is that if I start with some point cloud and just perturb it slightly, maybe by just some epsilon, it's some metric, then this topological descriptor, this persistence diagram, each of those points will also move by at most epsilon in some appropriate metric. So if we will wiggle those points here don't change too much. Otherwise, it will increase. And given two such diagrams, A and B, we can kind of overlay them. We can find some kind of metric between them, and then we can see how far the corresponding points are. There are some technicalities. For example, if the number of points is different, in particular, then we may match a point with this diagonal, which corresponds to things which are, haven't really, maybe you could think about those as things that, are die when they are born. So in a sense, we have this extra trick, which is kind of natural. And then we have a distance, which is actually a metric. So we can do a lot of, standard things with it. So, this distance just, in the end, this distance just returns a non-negative number, but as a distance, it's also a metric, so it's symmetric. Satisfies triangle inequality, so we can do a lot of nice things with it. So, the usual pipeline is that we start from a point cloud, we do this trick with growing balls. So we have a sequence of those nerves, which are basically complexes. We devise this persistent diagram out of this, and some people like staring at them, and some people like kind of vectorizing them and plugging them, feeding them into machine learning models. So this is what we do. So going back to our task, this is exactly the idea. We will have a bunch of inputs, which will be neural networks, which are either Trojan or not, and we will try to devise another machine learning model, another neural network, which will serve as a detector. But what it will, work with will be those persistence diagrams devised from some kind of point cloud derived from each neural network. Namely, this is the point cloud we discussed, which comes from the activations of each neuron on those images. And then in the end, we want our detector to reliably tell us if a given network was Trojan or not. So we train it on some training set, and in the end, we want it to reliably detect if a network was Trojan or not. So again, this network will work on those topological descriptors, on those topological fingerprints, which kind of abstract away from kind of the spurious information that is encoded here. So again, this point cloud here, it lives on this probability simplex. We can think about those guys as discrete probability distributions, or in other words, probability vectors. But we should decide some kind of distance or some kind of metric on this space. Those points are in Rn, so there is a very natural choice for doing this. So what kind of distance could be? What's the natural notion of a distance here? Okay, yes. I was expecting everyone to say the Euclidean distance, but I would much rather use something like cross entropy, or more. What I had in mind is the Kullback-Leibler divergence, which is the difference between the cross entropy and Shannon entropy, and it gives you something like a dissimilarity value. But yeah, that was obviously a very good bet. This has very nice information theoretical interpretations. In particular, we can think that the output of this Kullback-Leibler divergence, or relative entropy, is expressed in bits. There's some problems with it. In particular, it's non-symmetric. So in an ideal world, I would work with this. It is possible. I have some results actually which extend this whole idea of topological data analysis to things like the Kullback-Leibler divergence, and if you know about them, also all other gradient divergences. In practice, what we did was something slightly simpler. We used like an infinitesimal version of Kullback-Leibler, which is often called the Fisher-Rao metric. And there's a nice trick. We can take this data. There's a very simple isometry, and then we kind of map our data onto a unit sphere, and then we just compute distances there, which essentially amounts to computing the angle between points. So computationally, this is much easier. And essentially here we're in Euclidean space, which is much easier than working in with this object as much as I would like to just use this. So our detector, again, we start from an artificial neural network, which may have been Trojan. We cook up those activations, this point cloud, which distracts the activations. We choose a certain metric for our computations, and we devise this fingerprint, this persistence diagram. And this is what's fed into our detector, which we already trained. And it tells us if the network was Trojan or if it's clean. And I mean, the main crucial observation we got from this by analyzing how things work is that this initial kind of naive wishful thinking assumption was that we were right, and there is a significant structural change in this representation, in this co-firing activation information, and it is detectable by those topological ideas, and specifically Trojan networks exhibit significantly more prominent cycles in here, which corresponds to at the level of those diagrams, this corresponds to points which are much further to the diagonal, so they're much longer lived, or in other words, they have much longer persistence. So this was a very clear signal, which this detector was actually exploiting to detect those Trojan networks, and clean networks did not exhibit those cycles. So this was really a striking structural difference between this data derived from Trojan networks and clean networks. So the main thing is that using this topological information, as abstruse as it may sound, we were actually able to train a neural network which served as a detector for those Trojan attacks. And in this regime of limited data, it actually beat all standard baselines on all standard benchmarks. So we were really happy about this. So this is kind of this was the main takeaway from the paper. One follow-up thing we did, which is actually unpublished, is perhaps even more interesting because you can use this topological information. You can just, there are ways of literally checking what is this prominent one-dimensional cycle, and you can, if you think that each of those points here corresponds to a neuron, you can kind of pull back this information onto the actual neurons of the network. And the trick is that you would like to heal the network, so you would like to undo this Trojan attack. You could do this naively by just essentially retraining the entire network, but this is not much more efficient than training from scratch. But one efficient way of doing this, of healing this network, is by focusing on those neurons which were part of this topological signal that we detected, namely this one-dimensional cycle that was formed. So we can get our hands on the neurons which are kind of the most problematic, and then we can retrain just those neurons, so we can set up the training such that only those neurons, the weights of those neurons are affected, which leads to much more efficient healing of the network. So all the remaining neurons are unaffected, they're okay. We just have to make sure that those bad neurons get fixed. And like I said, so to me, I think this is a nice practical example in the context of machine learning, but to me it's also kind of a special result because it showed that the methods I had been working on for a long time can actually be used for analyzing high-dimensional data. And in the recent years, this field of topological data analysis has been growing. So if any of this sounds interesting, which often it is, for students who are more on the mathematical side, and they see that something they learned in those abstract classes, or about topology, or things like homology groups, they suddenly see that that those things are actually practical, and you can do something like that. Okay, I think this is all I wanted to say.
Any questions?
So, when we're talking about the radius of birth and radius of death of each topological feature, so I was sort of confused about that, but is that essentially saying that if we start increasing the radius slowly, you can see that some of those features start intersecting more and more? So can you explain further about what essentially is the radius of birth and death for, let's say, one given neuron in that example?
Oh, so I mean, it wouldn't be for a single neuron. So for example,
For one feature.
oh yes, I mean, for one what?
One for one feature.
Yeah. So in terms of so this would be one topological feature. So there is this one that you can think about, this one-dimensional cycle. So I can outline this whole here, and I can if I were to increase those for a while, nothing will happen. But at this radius, if you look at the union of those balls, which I didn't do here, there is no longer any hole inside that you can encircle like this. So this would be the birth, and this is the death. Of course, we could have many more of those features. What I didn't show is that at some point there would be a hole between those formed by those three guys, but only for a moment. So it would be much more short-lived. Okay. Any other questions?
Also, can you illustrate a little bit more why these kind of use the features or the appearance and disappearance of the whole? So what, second question is that, how do you map the neurons in the management? So So why are there features and how do these map neurons to implement?
So why are there features? You mean those topological features? Why
You have this radius of appearance and disappearance of the fault, right?
Mhm.
Then you use an AI to detect, to use these features for detecting
Yes.
attacks. So why can there be, I think it's related in variance, right? Because you said there are variance in other things. I really illustrate a little bit more what your feature to detect something.
Yeah. So I mean, so this is something I didn't really go into. So um, in a sense, I was for this talk I was satisfied with saying, well, there is a big difference between the diagrams, those persistent diagrams you get there, and this was enough for the detector to work. But and additionally, this information can be used to go back and identify those features. But as for an actual interpretation of this, I don't think it's really important that there is a cycle. But however, I really think about this at the level of the network is that there is some path which is path of neurons or essentially a subnetwork which is highly activated in the context of Trojan networks on Trojan examples. And then this cycle corresponds to co-firing of neurons which are kind of far away in the original architecture of the network. So there is a co-firing between neurons which are in the shallow layers and in the deep layers. So there's kind of an extra link, which in the paper we kind of argued that this is some kind of shortcut, which required more justification. But essentially, my main interpretation is that with this we kind of detect a subnetwork which is most likely responsible for detecting this special trigger which was used in this attack.
I think it makes sense. You're saying that it's like the relationship of neurons, right? Because you are looking at this all the relationship of neuron between shallow people. Your embedding space, right? So like the biological space, usually the point of probability distribution. How do we map in the parameter of the neurons?
Right. So I mean, so let me go back to this. So each neuron, like you said, becomes discrete probability distribution in this space, but what's really encoded in this are the activation strengths on each image. So in this space, each dimension corresponds to the activation on a single image that you show.
So if the distribution that activated the image, so you have the work and calculate
Yes.
distribution for the activation that was
so it's each coordinate of this point corresponds to the activation of a single neuron on a single image. So I call it a discrete probability distribution in the sense that I think about the coordinates of this point as the probabilities. And I mean, there are probabilities only so much, just like, soft predictions of a neural network are, probabilities just because we normalize it in a certain way. So there is this normalization which makes it, become a discrete probability distribution, but there is nothing else happening there.
The second question, since you already touched the trace these probabilities, have we thought about how to mitigate and solve because the continuous rate very into the body trying to use kind of probably analysis on alternate traces or generation.
No, we didn't think about this.
Do you think there's a link? Because my reason is because there are a lot of people in the field reviewing how to make sure that both important and talking about local time. So what is your opinion? Whether there's an important from
I don't think I know enough about Dawson Mission models to have an
observable probability within the environment.
I mean, I'll try to evade the question by saying, like here we have a very concrete pipeline. To what extent we could really, change it to kind of mix it up with something like Gaussian models, I just don't know. So, like in a sense, this is one way in which we do this. But I would be happy to talk to you about this. I don't think I want to commit to any opinion about this. I just don't think I know enough about why that's an issue.
So, when you're defending instead of this two dimension. I did space.
Oh, I mean, this is just a two-dimensional picture. We do this in very high-dimensional spaces. When I say I draw an edge, I mean, this is what we did here. You should think about this as some kind of abstract graph, and how you draw this edge is irrelevant. It's what's drawn here. You should really think about this as a graph, and I'm showing an embedding of this graph, but it is really an abstract graph. This edge just says that those two guys have an edge between them. I'm just drawing it here for so that you see it, but as a data structure, this would just be an edge from A to B. And that's it. And the same for this. This would, I draw it as a triangle in a concrete embedding, but it would just be an abstract triangle between 3 points and so on.
There are certain topological space seems really computationally expensive between changing the epsilon values, just that entire search. You just thinking about it.
Yeah, I agree. Like it seems, this is computationally heavy, but there has been a lot of work in making those computations feasible. There are a lot of shortcuts that people developed. So yeah, if you try to do those things kind of in a brute force way, it would be horrible. But for the last 10, 15 years, a lot of people, including me, have been working on making those type of computations efficient. So maybe that's all I should say about this. Right? I don't know how we're done.
We're over time, but I think it's lunch after this, so I think you're welcome to answer questions unless anyone wants to go to lunch.
I'm happy to answer, but I also would hate to keep people from getting lunch. So
Yeah, stay at your will, whatever you'd like to do. Yeah. Well, we have 6 minutes until lunch starts. And so I'm just saying there's no speaker like coming into the room right after you.
okay.
You can answer as much as you'd like.
So don't wanna pick anyone. Yeah.
Yeah, so I have a little bit, but I want to ask how exactly did you use your development and everything in field to solve the issue of the celebrating deafness?
So so the idea is that we have a network, and we wanted to distinguish between those networks, in particular Trojan and clean networks, right?
Okay.
And we had this initial idea that we would look into this kind of activation space where each point corresponds to the activation of a single neuron. But then, it's not clear how to compare those things. We have two kinds of geometric objects, but if you try to kind of compare them in a brute force way, like as if they were, I don't know, like 3-dimensional shapes, this is hard. But then the idea is that you can devise this type of topological fingerprint, which kind of captures the main properties of those guys and kind of abstracts away from everything else. So in particular, if there would be, this cycle here and not here, there would be a big difference between those fingerprints. And then we feed this information in some form to train the network. And, there is enough discrepancies between those fingerprints that this detector works reliably.
And those fingerprints would be, like, from what I understood, was that, like, with the point cloud, right? You basically, the issue of it was that depending on how you would rotate it, it would give us completely different things. So we needed to have something that would be like in that case, yeah, exactly. I just want to understand, like, how exactly, well, at what point do we notice that, like, that one's going to be Trojan and the other one isn't by just this?
Right. So in practice, it's not, this is something we just had to do experimentally. In practice, what happened is that Trojan networks, at least statistically speaking, would have those points which are further off from the diagonal. So if you think about what this represents, it means that there is a bigger difference between the depth and the burst. So it means those, they had a longer lifespan, which kind of means that they were, the difference of the radii between the burst and depth was larger. So essentially there were like larger holes in the Trojan, in the activation space of the Trojan ones, which were not present in the regular ones, at least statistically speaking.
Okay.
So this was,
and then that was the way that we were able to get back functions totally, like I said.
Yes. So in the end, like this new detector, this new neural network which we trained on this was able, the signal was strong enough that it could detect it. But once we noticed what the network actually does, because it was some simple model, we actually noticed that on average, or at least statistically speaking, there was this discrepancy in those fingerprints.
And is there like exactly a reason as to why that happened? Like a logical reason?
Well, we have some interpretations of this. So in a sense, this is what I answered, in a sense that one way of interpreting this is that, this cycle that is formed, this long cycle in the activation space, it's not really crucial that it's a cycle, but you can think about it that it's kind of let's say, a path with an extra kind of edge, which corresponds to, co-firing of various neurons. In particular, we interpret this extra, kind of the longest extra edge as a co-firing of neurons which are far away in the network, which is not something that would happen in the regular integrated model.
Right.
So, like, I wanted to know if this was a kind of similar to how, like, dimensional error reduction techniques and math where they try to like capture
Yeah, so UMAP is advertised as a kind of topological data analysis inspired method. Some ideas are similar between UMAP and those type of things, but I mean, other than this, UMAP is not so terribly different from TC. It's kind of a slightly upgraded TC in terms of how it works. It's definitely upgraded in terms of efficiency. So yeah, you're right that some ideas are similar. In the end, I don't think UMAP really, it mentions some of very similar objects. In the end, it definitely does not compute the same information. So in this sense, it's, the language you can talk about both is similar. Computationally, it's very different. The task is also very different just because, UMAP is just a dimensional reduction method. And here, in the end, we want to get this type of fingerprint. And there's also some work at the intersection of the two. So, for example, UMAP likes to overemphasize clusters or groups in the embedding and also holes which may or may not be in the original space. So there is work at the intersection where you may want to make sure that the topological features you see out of UMAP or another method actually exist in the original space. Even one person worked on this with the audience. So I should be bored all this stuff.
It's one just question. How do we come up with the words that were here in that word? And how do you actually hear in that here? Is it a standard word? How do you come up with it?
Oh, the birth and death. It is standard in my field. So I didn't invent them. This healing of the network. Yeah. So admittedly, I don't know if this is the standard way. I kind of but I think it makes sense. There's another word which I also like, which was actually so the guy who the guy who came up with the birth and death words also came with this name, and he calls this idea of using this information about cycles to kind of undo the damage. He called it cyclotherapy, which I like. So we use like inventing words.
Also like rolling radius, right? When you think about it, you really don't do.
Oh, sure.
It doesn't really go to tie and
Oh, of course. So I mean, yeah.
what's the one people going from field?
Well, I mean, like then, like this is kind of the mathematical underpinning on this. So mathematically, mathematically you can think about looking at all uncountably many radii, but then you really just store the information about when the topology changes, and then you can notice this. First of all, the largest change is roughly at the diameter of this point set, and additionally, there's only a finite number of changes just because the point set is finite. So those kind of things are kind of part of the mathematical theory behind this. And then the next step is to actually turn this into algorithms. And obviously the algorithm doesn't go through all uncountably infinitely many things. It doesn't even go, with some increment. We just know from the proofs, which really to look at it, in particular the delta.
I think you are already using that awareness in measure, right?
So version of this, yeah.
So you are using it and you shooting some space for really and the function of you some more transferable you actually have to imagine and more to be found that really necessary to go to in this scenario because you're already using that awareness.
Well, I mean, one funny, so in general, then, if you were in media space, you can compute the diameter of this point set, and you know that nothing is going to change beyond it, because if your balls are large enough that everything intersects, nothing else is going to happen. Okay, the scale of this is interesting because even though it's defined on a kind of set which is bounded in impedance sense, the volume of the field divergence can diverge to infinity if the second quantity is pending the boundary of the same case. Or in other words, if one of the components is tending to zero. So it is actually interesting if in this case, even though you have a bounded certain impedance sense, you may have very large, we may need arbitrarily large linear frequencies. But this kind of a very special case.
Oh, can you go to the slide about the magnetic space?
This one or this one?
The one. Yeah. So, like the way I understand it is that like our neural network will basically look like a set of points in like n-1 dimensional plane, right?
Yeah, essentially.
So now I understood that with each point, all of the coordinates of that point like sum up to one. So ideally, yeah, I get the intuition behind why we want to like use cross entropy, like find the distance between 2 points. But like the point that I was sort of lost is that like I don't understand why we need like a valid distance metric between 2 points. Because like at least like the example that you showed after is that we like construct like this like ball of like radius r and then we like find different intersections to like, build a graph. Like where is like the distance metric for that come in? Or why would we need like
Yeah, that's a good point. But keep in mind that it was not just a graph. If we, your observation was that if we only use the graph, then we would be missing, we would not get the same topology from the graph and the union of the poles. So it was actually crucial that we also encode information about intersections between triples, which which I drew as this triangle. So you need some kind of nicely defined space where you can talk about poles and intersections of poles. So you can't really do this whole thing, in a completely arbitrary setting where you just have some kind of pairwise value between points. This is really geometric in the sense that we need those poles and we need to be able to come up with intersections. And it's not obvious, but this is something you can do with KL, even though it is not a metric actually. So it's not symmetric, it does not give you triangular equality. But the poles are nicely defined. I actually kept them here for no reason. So they look something like this. And you can work with them and everything works. In the end, we did not use this because the software for this is still kind of rough. So in the end, we made the trick and we went for some kind of version of this which is easier to work with.
Okay, so is that metric basically like the angle that you find?
Yeah,
in
the end, yeah. So there is, so you could think about this as it is defined in some way in this space, but there is a very easy kind of to compute isometry between those spaces, and in the end, you can compute it much more easily here. That makes sense.
What's the one feature of using path and variance instead of in your system? Can we use like correlation coefficient that we use?
Yeah, so I mean, we tried a bunch of essentially the similarity measures for this. Some of them worked better. One thing which didn't work at all was the Euclidean distance. One of the popular correlation is worked roughly on par with this. So it's certainly not the only choice. It's just kind of a perspective I like. So if I were to choose, I would go with this, which is also consistent with what's often used in training of neural networks. So just have a chance of at least being able for many machine learning.
I just you were doing this for the small experiment quality models.
Well, by default, yes, but one of the points here is that if you just use the Euclidean distance scale, which technically you can, you would actually not get the result that we want. So we tried, our first idea was to literally just use the Euclidean distance here, and then the topological signal we were getting was not enough to get a reasonable detector. So the choice of the distance or the similarity level was actually featured here. But what we said is that instead of looking at the Gilder divergence or the feature round, you could work at you could look into some kind of correlation coefficient and it oscillates.
This feature round is competition evaluating the equilibrium.
Yeah, exactly. So this is often called either feature information, but as a metric, I think the standard name is feature row. So yeah, it is essentially it's the metric used by the hasher of entropy.
I always have this question: why do you need a law? Why do you need a law? the law we figure out and then I know that we have the law. And in the video and using the table, people have this law. So why having this law makes us a big deal? Makes you
Yeah, that's a good question. I mean, maybe a quick answer is, we come from analyzing what Shannon entropy gives you. So maybe not, I don't want to specifically talk about the log, but Shannon entropy has a very clear interpretation. It gives you the lower bound on how efficiently you can encode events and like this discrete probability distribution. So you can think about the log of 1 minus the probability as the number of bits you need to encode this, and then you just take an expected value of this, and this gives the lower bound on how efficiently you can encode things on that page. And then KL, which also uses the log, is the difference between Trojan entropy and Shannon entropy. So in a sense, it tells you how many extra bits you need if you're kind of confused about the probabilities of the events. So here we are assuming that we will be encoding things coming with those probabilities, but in reality we have to take the expected value with respect to the true probabilities. So this difference tells you how many extra bits you need.
I don't know if it is correct, but if you are using the linear division, this becoming previous.
Well, yeah, but we're in a finite dimensional situation, so everything is finite dimensional here.
Why not make this space better?
Why this is better?
Because you are using this metric, it's no longer distance like the mass.
Yeah,
it's not it's not metric. So why not use the metric such that this space is metric?
Well, it may have better mathematical properties. And let me, to answer this, you could ask the same question: why do we use, cross entropy to train networks and not just the, mean squared level, which corresponds to the square Euclidean distance? And I think the main reason, traditional would be that it just works better, right? And if you wanted to dig into this, one reason is that the gradient behaves very differently because this scale has different properties. So we could talk about this, but maybe this is enough to kind of evade the question. But it's not specific to this. People have been choosing KL or cross entropy in other setups, and it tends to work better than something similar happens here.
I'm interested in knowing the motivation, and was there any prior work that your research is based on, and how much novelty you have in this work?
Yes, obviously, this is a huge problem, and people have been working on this using different methods. There was a similar work where they also tried to use some topological technique. I think it was mostly concurrent, but they published before us, but their method didn't really work because they were missing a bunch of parts. As I understand it, they were kind of missing a bunch of details. So the idea was, to use topological data analysis methods was already kind of there. So we can't take credit for in first doing this, but it was the first method which actually worked reliably and get an actual, highly performing detector.
Okay, and this detector is working, and it works with every neural network, or is it works with a particular specialized neural network?
But I think the whole, like we decided for a bunch in the paper, we focused on ResNet and IntenseNet, which were kind of popular back then. But the whole setup is, at least in theory, it's kind of agnostic to the network. So as long as, you can talk about activations of, or feature maps and so on, but it should work.
Okay. Follow-up question on that is there is like essentially an architecture depends on image model and analytic model. How easily this experiment gave to being extrapolated with that means.
I have no idea if it would work. Like maybe, maybe what we observed was specific to those specific CNN architectures. But there is also nothing. I have no reason to believe it wouldn't work. Like, maybe we're lucky with, and it is a special property of those specific vision models. But like I said, like, the whole machinery we developed, like it's fairly general. So I actually don't know anything about, like I don't know anything about potential Trojan attacks on, for example, on LLMs and what it can be something similar. I guess they're different enough that, like anything could happen, right?
And so poisoning is a very issue with the learning models, and yet there are ways which is looking at that. So from what we have shown, it seems like it can resolve all those issues.
Well, I mean, so again, this is specific to vision models. I really wouldn't say that this resolves all the issues. I mean, like we're just saying that in specific, in a specific setup, we can, detect if it was poison or not, and we also showed that using this information, we can fix that more efficiently than the brute force way we need to essentially retrain all the neurons.
Okay.
So maybe I mean, really not go as far as saying that we fixed all the all the problems in Trojan detection.
Maybe the better efficiency is something which they still have to work. Better efficiency to get the better efficiency. And detection and reading areas. But that is something researcher like it is still something that you can work on.
Efficiency in one sense.
Like to requiring less resources in detection and basically doing issues.
Oh, that's true, yeah. I mean, this method, compared to methods which use which are outside of this limited data organic regime, like those methods are, horribly expensive because they just really essentially try to kind of reverse engineer a network by showing it really lots and lots of computers. So ours is more efficient in the sense that it can work with a much smaller set of images. But the computation itself, it is a heavy computation. And it is resource heavy. Now it would be easier. Now there are better tools on the TPA side, but it's still like it is a heavy computation building.
And I believe you also have when you do something like this, you also have an assumption that the detector itself is not violent.
Yeah, sure. Yeah, I mean we're assuming that we trust the people who. Like you have to trust someone, I guess.
That kind of approach you will always need to have.
Yeah, so like you don't trust anyone, but it's like, whatever you do, I think it seems to be right there. The question, do you trust me? But maybe this method actually, poisons networks.
Maybe your experiments were.
Oh yeah, or maybe I just made it up, right? Yeah.
So are you still planning to do more experiments and then just decide on different networks?
Yeah, this was more of a one-off project. I was after we did this, I was kind of interested in this, but now I think so much has changed that I'm no longer up to date. So I started work on different things. Like one really good thing which came out of this is that I did manage to interest Google in those topological things. So after I published this, I managed to get some funding on developing like those topological methods kind of geared towards this type of applications. So I mostly work on those kind of more low-level things related to making just those computational aspects more efficient. And then I sometimes work with people to apply these methods to different things. So this was with some of my long-term collaborators, but in this space of like Trojan attacks, this was like a one-off collaboration. And this seems is from which year? This was 2021.
So then, like there's a slide that mentioned permutation invariance, translation and rotations, like how you might handle that. So so one question I was that, would you really have to handle permutation invariance? Because like nowhere in the algorithm where I see that the order of points matter essentially. So that's something you have to explicitly handle for.
So what was the question?
So like, the way I understand like permutation invariance is that you can, if you have like a neural network, for example, the functions of different neurons can swap when you train the network twice.
Yeah.
So, but the points would still map to the same sort of set of points that you have, maybe in a different order.
Yeah.
So, would you really have to handle like permutation invariance in that sense? Because like the order of points in the algorithm, at least that I see, didn't really matter.
Oh yeah. So the point is that the property of this setup is that the order of the points doesn't matter.
Okay.
So this is like it's not something that you have to handle. Like it's just like an inherent method or inherent property of this setup.
Okay. And for the rotations and translations, so the way I understand about that is that if you have, let's say, a neural network, if you have two different neural networks that given the same input and output, roughly output the same thing, potentially they would have different neurons that like activate at different times, but their functionality is somewhat similar. In that case, in like the point space that we have, will they map to like somewhat similar points essentially? Or they won't, I guess, like technically, because both of them. So, I guess I can explain it better. So, if we have one neural network that, given the same inputs, produces some outputs, and we have another neural network which, when fed in the same inputs, produces different outputs. However, the neurons have different weights, and ideally would have different activation functions. Like this can happen, I guess, in the training scenario. And so, would your algorithm sort of differentiate between these two things?
Oh yeah. So I mean, since it looks at the activations, then it would because.
But their functionality is somewhat similar. So wouldn't that give like a sort of like their functionality would be like similar, but they would still be different according to this algorithm potentially. So would that not give a false sense of like differentiation?
Well, maybe. I mean, yeah. So I mean, it's so I agree. Like this method. You can have two networks which functionally are the same, so with the same results. But our method, this topological fingerprint is not about the output. It's not about the functional part. It is really about this more kind of mechanistic part where how was this? What was what were the computations, right? Or like at least some aspects of the computation. So yeah, if you wanted to tell if the two models do give the same outputs, I mean you can test it directly, right? But the method is more about like what was happening internally in the network, and and this was crucial for detecting those. If the model was Trojan.
Oh, so wait. If I understand, sorry, like the whole point was Trojan models had like more like cycles within like the topological representation that you had there, and so essentially you could like, predict whether a network is Trojan or not based off like the cycles that it had.
Yeah, exactly.
Okay, that makes sorry. I was like imagining as if like you're differentiating between the functions of like a normal neural network and like a Trojan neural network.
No. So this is this information, the difference in this signal is there are more cycles in this space, And this is based on the activations and not on how,
Okay, I see. Yeah, that's one option. So I'm pretty sure you said this in the talk, but when you were visualizing the neurons, was the set of images used to contain the fuzzy one or?
yeah. So in this setup, you don't have information which one is which.
Yeah.
And by the way, this Trojan pattern doesn't have to be so obvious as opposed to nothing. So this can be essentially anything. So you don't know what the trigger is, but you can have access to examples which contain the pattern. Otherwise, you will not be able to represent this.
Right. Did you try it without just like without any slogan things?
Oh yes, I mean for the we did compare on completely the data sets and yeah, it actually doesn't matter. I think like we from a certain point on, I think we listen to really yeah, so they actually don't basically
Don't try to do something in the space.
no, we should. It looks like it was more like one hour project in this started there.
I just saw your profile and I see that you're it's a little fun. What kind of current research you just when you did that? Are you ready to that?
I think it's a really lot. Like, I have a couple of students, but they would say really lot. Like I have currently two kind of official PhD students. I have one kind of unofficial undergraduate student I work with. One other kind of unofficial graduate study state. Yeah, just a small number of people. And well, so everything is related to those topological ideas. Often, with some intersection with machine learning, but that's really the focus is more on the well, not really, I wouldn't say mathematical, like it's more of the computational side, I would say, than the way, not necessarily pure math, but more on the algorithms which enable those applications.
So algorithms which we can have expected a unique program. Okay.
So, one thing I completely didn't say anything about other, like what the computations. So what you really have to do to efficiently get from a point cloud to something. So this is all, this is kind of at the core of my research, but mentioning any details about this is kind of pointless. Like I wanted to focus on like the highlight the way papers and these things can be used and how to exactly do it.
Converting the the node representation in vectors, is that something you find challenging or
You mean this part?
yeah.
Yes, I mean there has also been a lot of work on this because if you want fixed vectors, like if you do this naively, you just turn this into a list of pairs of points, like that's not going to work. So there are actually each of those arrows here, like there is a bunch of people working on this. So none of this is exactly trivial.
I think it will be more of a matrix or a vector use.
Well, in the end, well, I mean, it depends. There are some methods which give you a vector. The kind of one of the most natural things to do here is to actually turn this into some kind of image. Like
yeah, pixel. Pixel representation.
Yeah, some kind of pixelated representation. Some kind of heat map, and this tends to work well in conjunction with CNN. So, but there are many, a lot of people work on this. Two of the other professors that you were in this kind of space. I work more on on this part of the pipeline. So
Do you work with replication plan or
with whom?
replication plan?
No. What was it?
You can see it's basically, and that's what they need to comprehend the environment and those components.
Yeah.
So these things.
Yeah. So in the simplest case, you expand all of them in the same way.
And if you want to, oscillation.
Oh, oscillation involved in the rates. Oh, so so there are methods for this. This is the pipeline. What I described is the pipeline for like the kind of vanilla version of this persistent homology. There's a version of this called zigzag persistent homology, and this allows for in photos gradient to shrink and increase there. So here, as you increase them, you can think that you have inclusion from a small, inclusion between the unit of the pulse from the smaller radius to the larger radius. And in the zigzag persistence, you can have inclusions going both ways. So if at some point, algebraically, in the standard setup, you have linear maps between homology groups probably all going from left to right. In the it's called a zigzag because it depends on, those powers can go in any direction. And so both of them are.
And how is
Oh, I don't know. I don't know if this would be useful. I think there are some specific applications where you launch to kind of oscillate them. In this case, I don't think we would get any more information actually. But in some situations, you do well when your data is not really something it is.
I'm gonna end the recording now.
I think so.
Okay.